Hello, everyone. Welcome to this another remote session here. So in this clip, we are going to extend our discussion on red-black trees. So in the last session, we looked at how to perform the rotation procedure. So this time, we are going to extend that forward, where we are going to look at how to perform the insert operation today. Um, so just a quick recap or a recall to what we had discussed last time, right? So every node in a red-black tree is either a red or a black color. So meaning all the nodes has a color that is associated with it, right? And then the root node got to be black. All the leaf nodes got to be black. If a node is red, then its children got to be black, right? And then all the paths should have the same number of black nodes. So these are the top, I would say, top five properties of red-black trees, right? So it's important for us to remember these properties. So we take a tree, let us say a tree like this, and then we convert a tree like this, right? So we want to make sure the five properties are satisfied in that red-black tree, right? So after we perform the transition, let us say. Okay, so that's our goal here. So one thing that we should keep in mind when we want to insert a new node in a red-black tree, there's a two-step process. So firstly, we insert the node exactly the same way as we do for BST, right? So if we recall for BST, we go by branch, and we find the spot where we would want to insert a new node. Second thing to keep in mind is that all new nodes are colored red by default, right? So there's a red color that's given by default for all the new nodes. Let's call that new node as Z, and this Z should be of red color by default, right? And then we will, the idea is when we insert that new node as red, there could be two violations. One is the case one where the new node is is a root node, let us say, and you know that a root node can never be a red color, and it got to be a black color, right? But when we insert a new node Z as red, it's a violation, right? So it cannot be a red color. Second violation is that if a node is a child of a red parent, we know that a red parent can never have a red child, right? So that's against the property of a red-black tree. So we will also need to fix that. That's the case two. So case one, I think I already talked about that. So node Z is a root node, and it's a red node. So simply convert that from red to black, right? So it's just a change of color. So it's worth recalling last time we talked about a two-step procedure. One is recoloring, and the other one is the rotation, right? So we would need to do either of both or sometime both of those procedure in order to perform our insertion. So here all we are doing for case one is recoloring. Case two has interestingly three subcases. So where we call case 2.1 as uncle of a node Z is red, right? So you can see that the node Z's uncle, this guy, is red. If he's red, then we simply do the fix that's outlined in the algorithm right here. So where we say that change nodes Z's grandparent to red. So this guy becomes red, this guy becomes black, this guy becomes black as well, right? So the parent and uncle becomes black, grandparent becomes red, and then we kind of elevate the grandparent node as the new Z, right? So you can see that the new Z is the grandparent right here. Case 2.2 is where we say uncle of node Z is black and Z is the right child, right? So you can see that again, that there is a red problem right here, but this time the uncle is black, is a black node. So what we do here is then we are going to left rotate on this particular node, the parent of Z, and all we are doing is we are converting the problem from 2.2 to 2.3, where we shift the position of the node, which is of problem here, to be on the left side, right? By doing a left rotation, we simply shift the problem to be on the left side, and thereby it becomes case 2.3. 2.3 here, again, you can see the violation is on the left side. Uncle stays black, but it's on the left side, right? So if it is on the left side, the fix is quite simple again. All we are doing is we are changing the grandparent color from black to red, and then this guy, the parent, is changed to black from red, right? And then we are going to right rotate on the grandparent. So grandparent moves down, parent goes up. So B, C, A, and D continues to be the right child. Okay, so it's worth recalling that when we do right rotation, any child that is on the right side of that B should move right here, right? Because there's no child, then it's simply empty right now. Okay, so we had seen the algorithm and the step-by-step procedure, but then let's look at one real example to see how they are all connected. So let's say that we are given with this tree and we want to insert the node with the value 4, right? So simply what we do is we apply the BST rule. If you recall, we ask a question starting from the root, is it on the left or right, right? So 4 got to be on the left side. So 2, is it on the left or the right? It got to be on the right side. 7, we ask a question, is it left or right? It got to be on the left side. 5, we ask a question, is it left or right? Because it's node 4, it got to be lesser. So we are going to find the spot where we insert 4, right? So we got 4 hooked up to 5, and thereby there's a new parent-child relationship. But keep in mind, there is a red-red violation right here, right? So that is what we are talking about. So we want to fix that violation because it is a red-red kind of violation right here. So first thing first is we need to identify what's going on with that particular node 4, right? So node 4 is Z, uncle is red, so thereby we know that it is case 2.1, right? So the violation is at node Z, uncle red, so simply we need to change the grandparent color to red, parent and uncle becomes black, and then elevate the grandparent to be the new Z. So we do that right here, so you can see that we change the color, black and black, and this becomes red, and this becomes your new Z, right? So the grandparent becomes your new Z right now. So the grandparent is your new Z, but keep in mind, there is another violation right here, right? So it's a red again, and this is why we talked about it last time. There was a good question from one of our class member, should we do the fix upwards? Right, so we got to do the fix upwards at some cases because there might be a red violation upwards, right? So because there's a violation upwards, we need to fix that particular problem. So this time we can see that the uncle is black, and this is the right child. So case 2.2. So simply it means then we need to shift the position of the problem to the left side, right? So we shift that by doing a left rotate, we change the position. Now it would be case 2.3. So you can see now that we had done the shift. So now you have the position on the left side. There's a violation right here, left, or I should say red violation. Uncle is black. So then it becomes the case 2.3. Right? So case 2.3 simply means then is we are going to change the color of the parent to black, and then this guy becomes, grandparent becomes red, and then we right rotate them, right? So meaning 11 goes down, 7 goes up. So you can see at this point we are able to perform all those operation very well.